Our next presenter is Dryver Huston. He's a professor of civil and environmental engineering at the University of Vermont. He received his BS at the University of Pennsylvania and a master and PhD for the University of Princeton. He has authored a book called Structural Sensing, Health Monitoring, and Performance Evaluation. And his presentation is called Bridge Deck Underside Inspection with AUV Mounted Sensor.
Okay, well, that was a great talk we just heard from Eric, and we'll talk just for a couple minutes about it. Largely a follow-on or a subset of the topics he was discussing. This is largely a TIDC project with University of Maine, University of Massachusetts Lowell, and University of Vermont. Okay, so here's the basic motivation is that we saw a picture from Eric's talk. The undersides of bridges are largely neglected. The top sides have been studied for years and there are major maintenance problems, but the underside also can be a problem and you get spalling. And here's an example of a bridge. Of course, these snooper trucks, as we heard earlier, have issues. And so can you do a UAV? And so here's a custom UAV built by a senior class at Maine for this application to come up and inspect the undersides here. And that was about a year and a half ago, 2 years ago, we prepared that slide. And in the summer, a little more happened. In Vermont, they started, this is not that uncommon, but we're putting wood to prevent the concrete from spalling and falling on cars. Also very innovative, entirely different topic, but quite successful use of art on pillars to prevent graffiti. This seems to be a nice way to go. And then about three weeks ago or so here in Maine, Falmouth, a chunk fell off a bridge and damaged a car. No one was hurt, but it looks pretty gnarly there. And not sure if this is accurate, but the news reports say that this bridge was recently inspected in April and the concrete looked good. So this is an interesting thought if that's really true. The overall concept, as we heard from Eric, use UAVs to inspect the underside of bridges. There's multiple technologies. Our group has been looking mostly at acoustic. Yang's group in Maine has been looking at some microwave systems. Acoustics, long standard technique for assessing concrete. If you can get good sound, you can tap on it, roll on it, chain drag, and it doesn't take much training to tell the difference between the two by the way they sound, whether it's healthy or unhealthy subsurface cracks. And so can we extend these techniques to the bottom side of a bridge? Sort of the thought with the UAV. And here again, different acoustic sounds with damage. It's quite distinctive. Okay, so automating chain drag and tapping starting to come along. A few examples. Here's a group in Utah did this about 4 times a second, a little slow for the underside of bridge decks, but at least demonstrated the viability. These fellows in Canada have a patent to do this. Haven't seen them actually deploy it, but they're making some progress. Again, their emphasis is, like Eric said, on the artificial intelligence and data processing. Also, if you're working under bridge decks, you need protection around your propellers, otherwise you have issues if you crash. Looked at all different ways of testing acoustic sounding under bridges. The student that did this actually was a military contractor, so they like these charts where you rate things high and low, and essentially came up with tapping as the winner. And here's the tap. Initially thought we needed high fidelity, expensive high fidelity and heavy sensors. We think we can get away with cheap ones. Here's another example of one of these delaminations that has since been covered by wood, tapped it out. So that thing was hanging loose there for a while, several months anyway. How do you test it in the lab without turning it into a whole research study of testing defected concrete in the lab? But very interesting how you actually make a delamination in the laboratory that's effective, and ended up trying several methods. Frozen ice was a fun one. Styrofoam seemed to end up working out the best. And built some slabs to test those. And the damage and undamaged is very distinctive to the ear. And can we build a drone-based tapping mechanism? So this is sort of a not quite drone-based, but a lead-in. No. What else is doing? Okay, I can just keep going. Anyway, the tapper works fine, and we can make it work. And then, but that was too lunky. And so now can you make a lightweight one, put on a drone, and adapted a mechanism from a paintball gun to shoot a steel ball into the drone and then recover it. So you're not losing ammo, but you're shooting and recovery. And so here's the Longstem Ball that we can recover and print this all out of lightweight 3D material. And there's the ball. Originally we had a piezo in it, but dropped that, didn't really need it. Did a weight analysis. We've gotten this down even further, but it's about a pound still, total weight. We think we can reduce that further. The electronics start getting heavy. Propeller noise, is that an issue? Yes, indeed, the propeller noise is an issue, but we can work around it. It isn't a showstopper by any means, and that's what this study showed here. Also, the tapper makes noise itself. And you want to compare that to the ball tap, and again, we can work around that. So that's very successful. And then here, looking at the different samples, indeed, we can hear with our ear that they're different. The tapper can make different sounds, and the signal processing can detect the damaged versus undamaged cases. There's the tapper in the lab. This is just ordinary spectrum. It's not so distinctive. There's some other methods. One called the Hilbert Huang transform, developed by NASA about 15 years ago, seems to be the strongest discriminator. And so we've got some nice signal processing that can now tell the different cases. And here, after a little bit of signal processing, you can really tell in color now what your ear can hear nicely. This might be, again, a great opportunity for upgrading with AI and machine learning techniques. And can test it in the lab. And then this past couple of weeks, we've been looking now to start deploying in the field. And so we've done some fit the tapper on a drone, done some laboratory testing, and have identified a bridge site. We're going to have to put a cage around or use the main drone, but a bridge site with easy access by walking without a snooper truck. Also, just a comment. This is over the La Platte River Bridge. The La Platte River, it's a 3-span bridge. The river usually runs through the center span, and we'll test here on the side. But about 3 weeks ago, we had a flood. You can see how high the water came up, about 20 feet higher or so, or seemed like 20 feet. But it's all covered with mud when we were out last week, so that'll be that's a concern. But and also anti-graffiti measures, again, don't want to harp on that too much, but are something to think about. And conclusions, we've got a tapper mechanism, hope to be testing later this fall on that bridge. And we'll try to find some of those delams. Thank you.